Hi, in this mini lecture I'd like to introduce hazards. What the hazards are? The hazards are exceptions to the Boolean algebra rules which occur in the real devices, I mean the electronic ones, when you implement your system in hardware. And hazards can be divided into two groups, two kinds: static hazard and dynamic hazard. What static and dynamic hazard means, I will explain using an example. Let's suppose it is a system, a combinational block containing a number of inputs, A, B, until Z, let's say, and a number of outputs. We are interested only in one of them. It is y output. It can be described in Boolean algebra. Yes, equation. As usual, you can find equation. It can be simple or more complex, but you can draw the equation for it. And then let's assume that the values of the B to Z inputs are static. One pattern, a selected pattern, that doesn't matter which one. And you change the value of A, having 0 first and then 1. It is a change on A without changing any other inputs. Okay. And from the equation, it results that the change of A doesn't change Y. Y shouldn't change from the equation. So drawing this on the timings, on the time axis, you've got A signal which is initially 0, then 1, the remaining are static, and we are interested in Y. Let's suppose that it is 1 in this situation when A was 0 and should remain 1, shouldn't change. It results from the Boolean equation. But in a real device, you will observe if there is a static. It can be or not. It depends. But if there is static hazard, you will see something like this: a short glitch of logic 0 before Y returns to its logic 1. So it is an unwanted glitch which is not consistent with Boolean algebra, not consistent with Boolean algebra rules. Because from Boolean algebra equation, for all the times, the signal should be 1 without an exception. So it is the illustration of static signal. What about dynamic static hazard? What about the dynamic one? The word dynamic means that from the equation, now we will be dealing with dynamic. So let's suppose that from the equation, the system should react on the change of A, and it is a Y prime. It is a Y prime. When there is another equation which tells you that the system should change its output Y. Output Y should change. Okay, this is from equation, from Boolean algebra equation. But what you will see in the case of dynamic, and that's why the system should change its value on one of the inputs, and you will observe something like this: multiple glitches preceding the stable zero, the stable change of the signal. Yes, multiple glitches, not only one. One glitch was in the static. One glitch not compatible, not consistent with Boolean algebra, but here you've got multiple glitches preceding the change of y, or stable change of y. Okay, so let's assume that we'll be now dealing with the dynamic, no longer dealing with this. We are only interested in this course with in static hazards, and I will show you practical examples. And let's start with the main cause of hazard behavior is a delay which is introduced by gates, by logic gates into the signals, into the logic signals. Okay, so let's suppose we've got the smallest gate, and its delay value is represented by TP, propagation time. Okay, it is a delay. What it means is that if you would like to draw x, let's say x is this, the not x will be delayed version of inverted x. So it is a 1, and here there is a change, but the corresponding change on the output will be a little bit later. And this period of time is exactly TP, is the most important dynamic parameter of the gates. And the same is true for this change, 1 to 0 on x. There is a delay again. These delays can be different, but we will treat them as exactly the same. Sorry. Exactly the same. Let's say this is all right. All right, and let's do another example. Let's feed these two signals. It is not a very practical example. I will switch to more practical in a moment, but to show you the consequences of having these delayed x and not x is to feed it into an AND gate. So now I am calculating what? From Boolean algebra from point of view, I am calculating product x times not x, which is, of course, as you know, 0, should be 0. So y should be 0 all the time. Okay, y should be 0 all the time. The theory is y is always 0. But theory. And in practice, look at these signals. There is a delay between x and not x. So look at this. They are both equal to 1 for a time. 1 for x and 1 for... The same is true here. 1 for x and 1 for not x. So x and not x not always are of different logic values. They are simply, they can take the same values. Here, both are equal to 0. But if you multiply two zeros, you get the same 0 as in the theory, and the theory tells you. But in this situation, you will observe glitches, which are not consistent. So 0, but here 1 on y. And again 1. So each change from 0 to 1 on x generates one glitch on output, which is not compatible with Boolean algebra. Static hazard. This results from the different delays of x and not x. And this is the rule for the static hazard. The existence of the signal and its inversion has an influence on the output gate. And let's switch to another practical one. As you remember, I hope, the multiplexer of minimum size is the following, having only 3 inputs. One is x1, x0, and select line is a single and single y. Okay, let's implement it using the Boolean algebra equation. You know, I hope, that it is not s times x0 plus s times x1. And the logic diagram is the following. You've got the s and not s here, s and not s, and you must have 2 gates, 2 AND gates. Not s is multiplied with x0, that's why it is x0 input, and s is multiplied with x1, which is this one, this x1 input, and 2 outputs are connected to the inputs of 2 input, and we've got y. All right, so let's do the experiment and assume that you've got a static one of x1, static one of x0, and here on S you change, you select 0, 1, x0, x1, x0, x1, x0, x1, and so on. You change the selection of the 2 inputs from 0 to 1, from 0 to 1, from 0 to 1, and you observe the outputs. In theory, what the output should be? Because you've got 2 inputs equal always 1, 1, you expect to have a static 1 without any changes. So y in theory should be 1 forever, even if you change, yes? Because the 2 has a, but let's analyze it taking into consideration TP. Let's assume that all the gates have the same TP. It doesn't matter, the value of TP is not important. We are doing an analysis in qualitative manner. So let's start with the signal. Let's label this not S, and this is S, and this is not S prime because it is delayed S per S naught, and this is S prime because it is delayed S. But you can see that not S is delayed by 2 TP before it reaches the output gate. That's why I am drawing S prime as being the following: 0, 1, 0, 1. That's enough. 1 TP comparing to S. Okay, 1 TP compared to S. And S prime is delayed by 2 TPs, so S prime inverted. So inversion is the following, but you've got a greater delay. Okay, they are shifted. It is S prime inverted. There is another one. And now what you do is to produce Y, which is a sum of these two, a sum. So let's calculate 0, 1, 1, 0, 1, 1, and 0, 1, and 0. So if you add, you've got 1, 1, 1, 1, 1, 1, 1, stop. You've got 2 zeros here, 2 zeros here. So you've got a glitch, which is in this case level 0 glitch. Okay, and on each falling edge, on each change of S from 1 to 0, you will get a glitch which is not compatible with the theory, because in theory, when you